George Akbar, and welcome back to Galaxy Today. In a galaxy that's expanding every second, the ability to transverse it is getting harder and harder. But physicists have thought of a new idea to transverse the vast distances of empty space, and it might actually be easier than they thought. Starships powered by tiny black holes. Physicists Lewis Crane and Sean Ware-Smolin have outlined how to do this, and this could have profound effects. To discuss this topic today, we have renowned physicist Alberto Onestone to discuss these ideas with us, and the issues surrounding long-distance space travel. Welcome aboard, Alberto.
Thank you, George.
Well, what are the issues we need to look at with long-distance space travel powered by black holes?
I guess the first thing you need to look at is that all living things are vulnerable to cosmic rays, as well as all the other radiation that's in space. These cosmic rays can have damaging effects on life when travelling in deep space. And what that means is that there's a heavy amount of shielding required on smaller crafts that travel in deep space. This shielding can greatly increase the mass of the ship, and thus the amount of energy needed to propel it into deep space. This is why we think much larger ships, which already have this shielding inherently built into them, will be much more cost-effective for long-distance space travel in the future.
We have just received a tweet from one of our viewers who says, "Antimatter annihilation worked just fine for the Enterprise. Why not just use that? Live long and prosper." From @Spock at Twitter.
Yes, I'm happy to answer that question from Spock. The problem with antimatter drives lies actually in the making of the antimatter, which consumes enormous amounts of energy. When you add to this the challenges of storing it on board the craft, you can start to see the problems that are inherent with antimatter drives. This is where the use of small black holes comes into the equation. Stephen Hawking developed the theory of Hawking radiation. Now, whilst black holes are famously associated with consuming everything in their paths, mass, energy, even light, Stephen Hawking proposed that even black holes must leak photons and other particles slowly into space.
And how does this help us travel across space?
Well, George, the smaller the black hole, the more power it emits, and thus the more particles can radiate from it. So a small black hole spews out large amount of energy. So in fact, in this case, a black hole slightly smaller than an atom would be able to power an entire starship. This drive would supply much more energy than Spock's antimatter drive.
So we need to create black holes. But aren't black holes dangerous, even small ones?
Black holes created on Earth would be too small and decay too rapidly. In fact, they decay in a fraction of a second. That's why they pose no threat to us. For these black hole drives to work, we'd need a black hole slightly bigger that would produce enough Hawking radiation to drive a large vessel across space. However, through the work of Crane and Westmoreland, we have calculated that it is within the laws of physics to do this.
So how big a black hole are we talking about here?
Just a few attometers.
What's an attometer?
It's a nanometer. To put it in scale, it's the size less than a proton, but its mass is of millions of tons. If we were able to get a black hole of this size, we would be able to extract large amounts of power from it for around about a decade.
So how is this all done, Alberto?
Well, firstly, you need to get a set of gamma ray lasers powered by a gigantic solar panel array orbiting a nearby star. You then concentrate those beams together and you create a small black hole which emits the radiation required to propel the spaceship across the universe.
Right. So what's the catch then?
Well, there is a small catch, George.
Go on.
Well, George, the power created will only be realistic if the physics of the mathematical framework of supersymmetry is true. But we just aren't 100% sure if the physics of that theory are correct yet. It's not yet proven. Supersymmetry means that for every matter particle, there should be a force particle, and for every force particle, there should be a matter particle. We are smashing particles at the LHC to see if this theory of supersymmetry is true. The whole idea could be wrong, but we just don't know. But it's important that we find out. Otherwise, we won't be travelling anywhere. If supersymmetry is correct, then we'll have a major clue in solving quantum gravity, as there will be twice the amount of matter in the universe than originally thought. We just can't see it. And thus the chances of us building a black hole-powered spacecraft will be much, much brighter.
Sounds like you have a lot of work to do, and we look forward to seeing the results in the future. I hear that Dagobah is nice this time of year, but it's just so far away. That's all we have time for on Galaxy Today. Thanks to our guest, Alberto Onestone. And remember, if it all seems too easy, it's a trap!